Today's video is about Claisen condensation reaction, and just like how I did the video on Aldol condensation reaction, I'm going to talk about the mechanism that comes with it. Okay, I'm going to explain the mechanism step by step for you to understand. All right. Now, before we dive into it, I would like to remind you not to forget to subscribe to the channel if you are new. Okay, and if you have already subscribed, then thank you very much. I'm so grateful. Right, don't also forget to like the video, share it with your friends, and comment on it. All right, and most importantly, turn on the notification bell. All right, so that anytime I release a new video, you'll be the first person to be notified. Okay, good. Now let's look at what we have today. Claisen condensation reaction. Okay, the first thing that I would like to talk about is the reactants that we are going to be using in here. Okay, unlike Aldol reactions where we use aldehydes and ketones, okay, Claisen condensation reaction deals with esters. Okay, so we are going to be dealing with esters as our reactants. All right, and then followed by the condition. Talking about the condition under which the reaction occurs, okay, we are going to be using a base as the catalyst. Okay, just like we saw in the Aldol reactions, here too we are going to be using a base. The only difference here is that the base needs to be equivalent to the ester that you are using. Okay, so for example, if I am using an ester that has ethanate as the alkoxy part of the ester, then my base must be corresponding. Therefore, it must be what sodium with ethanate. Okay, if I am using an ester that has methanate at the end, then I need to use a base like sodium methanate. Okay, if I'm using an ester that has propanate, then I need to use an equivalent base of what? Sodium propanate. So the base that you use in Claisen condensation reaction need to what? Correspond or must be equivalent, okay, to the ester that you are using. All right, that is the only difference here. Also, the Claisen condensation reaction occurs in the presence of what? An acidic environment. So we use hydrozonium ion as the representation. Okay, we use the hydrozonium ion to represent it. It occurs under this condition. Okay, using what? The base as the catalyst. All right, good. Now I would also like to speak to the fact that there are two different kinds of Claisen condensation reactions. We have what we call the self-Claisen condensation reaction, and we also have what we call the cross or mixed Claisen condensation reaction. All right. For the self-Claisen condensation reaction, the ester that you use will end up reacting with itself. So, for example, if I use an ester like this same ester will end up reacting with itself in order to establish our condensation product. Okay, but then if you are dealing with a mixed Claisen condensation reaction, then it means that we are going to be working with two different esters. All right, you are going to be working with two different esters. And then one exception to is that even though Claisen condensation works only with esters, okay, for the mixed Claisen condensation, you can have a situation where a ketone will end up reacting with an ester. Okay, and for that matter, the only reason why that can happen is when your ester does not have an acidic alpha hydrogen. So it means that the ester you are using, it must not have any acidic alpha hydrogen. Okay, so for that matter, the ketone will now be the one to form the carbanion and rather attack the ester to form the Claisen product. Please, are we following? Good. Yeah, so now let's dive into the mechanism proper. Okay, I'm going to use a simple ester like I'm going to use a simple ester like this one, and then what next do we have to do? We need to establish the conditions under which the reaction is occurring. Okay, so this, as I said, you need to use an equivalent base, right? Because I have ethanate here or ethoxide here, what happens? I'll end up using what? Sodium ethanate. Okay, this is my first condition, and then the second one, it has to occur under the presence of what? An acid. Okay, aqueous acid. Okay, good. Now the first thing that happens in this reaction has to do with the formation of what? Carbanion or an inolate ion. Okay, the formation of a carbanion or an inolate ion, it is the same thing that happened in Aldol reaction. When I made a video on that, I explained vividly how the mechanism occurs and how carbanions are formed. Okay, so in this particular video, I'm just going to give you the quick representation of it. Okay, if you really want to understand how carbanions are formed using the bases, then I would advise that you go to the description section. I'm going to put the link to that video there so that you can just click on it and go directly and go and watch. Okay, good. So now what do we have here? I'm going to dissociate my base. If I dissociate my base, I'll end up having sodium ion here, and then my ethoxide ion also here. Okay, now this ethoxide ion here is what I'm going to use for the formation of the carbanion. All right, now how do I form the carbanion? When I come to my molecule, all right, this is the alpha carbon, and the alpha carbon has 3 hydrogens on them. Okay, these hydrogens are very acidic. Okay, so it makes it easy for our ethoxide or our base to come and abstract. All right, and how does the abstraction occur? The base picks the hydrogen breaks its bond onto the carbon to establish a negative charge on the carbon. Okay, now when that happens, we end up having a carbanion. This way, we have a molecule that is having a negative charge on an sp3 hybridized carbon. Okay, so this is our carbanion. All right, now the next thing that you also have to do is you establish a resonance system. Okay, you need to be able to generate a resonance pair for this carbanion to ensure its stability. Okay, so I need to bring my resonance sign, and then how does resonance occur? This negative charge here has to be delocalized into the system, and then to prevent carbon from having more than 4 bonds, what do? I break the pi bond onto the oxygen. All right, when that happens, I end up forming what? An inolate ion, and this is how an inolate ion looks like. So this is my resonance system. Okay, now because it's a self-Claisen condensation reaction, okay, this either this or that, either the inolate ion or the carbanion, okay, will now go back and react with our original molecule, the unreacted one. Okay, now in the reaction we usually use a base. This kind of base is a weak base. Okay, and this is a weak base because we don't want the base to completely deprotonate or remove all the alpha hydrogens on all the molecules. We want some of the molecules to be remaining in the solution unreacted, so that we can end up reacting them with our carbanions or our inolate ion. Okay, in order to form the Claisen product, right? So that is the main reason why we are using a weak base. Okay, so because the base cannot deprotonate all the molecules, we have some of them remaining in the solution. Okay, so what is going to happen now that we have formed a negatively charged species here? One of this will go and react with our starting molecule, the neutral starting molecule. Okay, so it's your choice. You can either decide to work with the inolate ion or you work with what? The carbanion. Okay, but for the purpose of this video and for clarity's sake, I'm going to use the carbanion. All right, now this is my carbanion here. Okay, now what do? The carbanion comes to react with our starting material, the neutral one. Okay, it comes to react with the starting material. And how does it react with it? The negatively charged carbon atom, okay, reacts or attacks the carbonyl carbon. Okay, so this is how it's going to be. It attacks it this way, and to prevent carbon from having more than 4 bonds again, we break the pi bond onto the oxygen. Okay, now that we have established this, all right, what happens? We end up forming what? An intermediate product, which we call a tetrahedral intermediate, right? Drawing the tetrahedral intermediate is what confuses a lot of students, so pay much attention here. All right, all you have to do, okay, is just locate the 2 carbons that are connecting to each other. All right, locate them. This carbon is connecting to this carbon, so let me label this. Let me say this is carbon 1 and this is carbon 2. Okay, the carbon here is carbon 2, and the carbanion or the negatively charged carbon here is carbon 1. right? So I'll just come and draw a 2-carbon system and label them carbon 1 and carbon 2. Okay. Now I'll just have to come and look at the substituent attached to each of these carbons and then do likewise to them. Alright. So if I look at carbon 1, what do I have? I have a carbon bearing double bond oxygen, right? So if this is carbon 1, I need to draw a carbon that is bearing a double bond oxygen, and that same carbon is having what? An ethanate or ethoxide attached to it, which is what? This one. So this part which is attached to the carbon 1 is what I just drew over here. Okay. Now if I look at carbon 2, what else do I have? Carbon 2 is directly bonded to an oxygen that is having a negative charge. Now you know the reason why the oxygen is having a negative charge on it, right? Because as the carbanion attack the carbonyl carbon, we need to break the bond onto the oxygen. That's how come the negative charge on the carbon on the oxygen. Alright. Now that same carbon 2 is having a methyl group attached to it. So I'll just draw it here. Okay, and it is having a bond with what? This ethoxide group. Okay, so it's also going to be written here. So now this becomes our tetrahedral intermediate. Okay. Now what happens within our tetrahedral intermediate? It is highly unstable. Why? Because there is a negative charge in it. Okay. So we need to bring it back. We need to stabilize it. Right? How do we stabilize it? The stabilization is done by bringing the negative charge back into the system. Okay. So the negative charge on the oxygen, we bring it back into the system to establish a double bond here. Okay, in doing that, we need to kick off this good living group. The ethoxide group is a very good living group, so we need to kick it off in order to establish a stable carbon system. This carbon, if we break this bond back without breaking this one, we end up forming 5 bonds, which is not possible. Alright, so as we bring the electrons back into the system, we need to be able to break out this ethoxide group. Okay, now when this ethoxide group leaves the system, what do we get? We end up having a product like this. Yeah, so this is the product we form plus our ethoxide, which is negatively charged. Okay, good. Now what happens? The next thing that happens is that because this ethoxide group is negatively charged, it is highly unstable, right? So it comes back to pick a proton from the system to achieve stability. Okay, now if you look through this system, okay, this alpha carbon, the alpha carbon in between the 2 carbonyl system is highly acidic. The hydrogens attached to them are highly acidic. Alright, so they can easily be abstracted by our negatively charged ethoxide group. Alright, so it comes to abstract this proton, and as it takes it, the proton breaks its bond onto what? The carbon to establish or to form another negatively charged species. Okay, now let me rewrite it clearly for you to see. Good. So as our negatively charged ethoxide group comes to pick the proton breaks its bond onto the carbon to form another negatively charged species. Alright, and how is that species going to look like? Look at the direction of my arrow. I'm going upwards. Okay, so this is transforming upwards, right? So this is what we are going to get. We end up having a molecule which is having a negative charge in the middle here. This negative charge is as a result of the proton that was the ethoxide abstracted, plus what? Now it becomes what? An alcohol group. It becomes ethanol. Why? Because it has now taken a proton from the system. Okay, so it has now established stability. It is now ethanol. Okay, and then at the expense of becoming ethanol, it's caused this molecule to become what? Unstable as well. Okay. Now the good news is that I'm going this way. Okay, the good news is that because my molecule here, okay, is in the presence of a hydrozonium ion, or it is in the presence of an acid which is what? Rich in protons. Okay, this acid will end up donating proton back to quench this negative charge over here. Okay, so what happens is that our negatively charged carbon comes to what? Abstract a proton, okay, from our hydrozonium ion, okay, so that it can quench the negative charge here and become what? Neutral. All right, so when that happens, we end up having this. Good. So now this is our final product. This is what we call the Claisen condensation product. Okay. I'm sure you're able to understand what I explained from the beginning till now, right? And then if that is true, then I am grateful for the fact that you're able to stay with me from the beginning till now. Thank you very much for watching the video. I pray that you find something positive out of this, and then it helps to increase your understanding of Claisen condensation reactions. All right, this is a mechanism behind the Claisen condensation reaction. It is similar in the cross Claisen condensation reaction. Okay, so any question that you meet that involves esters, okay, two esters, whether two different esters or one ester reacting with itself, that involves the use of a weak base like sodium ethanoate, sodium methanoate, and co in the presence of an acidic medium like a hydrozonium ion, then you are welcome to use a Claisen condensation reaction mechanism. All right, and then if you are familiar with this mechanism, it will be easy for you to work with any other question that you'll be given. All right, thank you very much. I'll see you next time.